June 7, 1944. 8 miles inland from Omaha Beach. Lieutenant Klaus Zimmermann of the Luftwaffe 3rd Fighter Wing stares at aerial reconnaissance photographs that make no tactical sense. Yesterday, this Norman pasture near Saint-Pierre-du-Mont was empty farmland, checked and confirmed by Luftwaffe reconnaissance at 1700 hours. Today, American fighters are landing on it. The photographs show a runway, 1,500 meters of steel matting where cattle grazed 24 hours earlier. Zimmermann's hands tremble as he counts the aircraft. 37 Republic P-47 Thunderbolts, not damaged stragglers making emergency landings, combat-ready fighters, refueling and rearming for their next sortie against German positions. The distance from the beachhead eliminates any possibility the Americans trucked in prefabricated sections. This airfield was built here. In one day, his commanding officer dismisses the report. Impossible, he writes in red ink, across Zimmermann's analysis. Airfield construction requires weeks, even months. The Americans must have concealed existing facilities, but Zimmermann knows these fields. His unit photographed this exact location every third day since March. There was no airfield yesterday. There is one today. What Zimmermann cannot understand, what German military doctrine has no framework to process, is that American aviation engineers don't build airfields the way European military tradition assumed such things were built. They don't excavate foundations, pour concrete, or construct permanent facilities. They transform dirt into operational runways, using methods developed in 38 days of frantic innovation, then proven across Pacific Islands, where speed meant survival. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Wehrmacht had studied American industrial capacity with Germanic thoroughness. German intelligence officers knew about Detroit's factories, Pittsburgh's steel mills, and the massive production lines churning out aircraft and vehicles. What they failed to grasp was that American engineers approached construction problems with the same mass production mentality that built those factories. 3,000 aviation engineers, equipped with revolutionary surfacing materials and construction equipment no other military possessed, were about to prove that airfields could be built faster than German staff officers could process the reconnaissance photographs confirming their existence. June 6, 1944. H-hour +3. The 819th Engineer Aviation Battalion lands on Utah Beach with a mission that contradicts everything their West Point instructors taught about military engineering. Build an operational emergency landing strip by nightfall. Begin construction of an advanced landing ground capable of handling fighter operations by June 14th. Do both, while German artillery positions 200 yards away are still occupied by enemy forces, actively firing at your equipment. Captain Robert Morrison watches his men unload bulldozers under machine gun fire. The Yale civil engineering graduate understands what makes this different from any construction project in human history. Normal airfield construction follows methodical sequences. Survey the terrain, excavate to proper depth, stabilize the soil, install drainage systems, pour concrete or lay asphalt, allow curing time. The process takes a minimum 6 months for a basic fighter strip. Morrison's battalion has 8 days, not because headquarters established that timeline through careful planning, but because tactical air support must operate from forward positions, or Allied ground forces will face German counterattacks without close air support. Fighter aircraft based in England face fuel limitations that restrict their combat radius to approximately 150 miles. Normandy's beachhead extends exactly 12 miles inland. Every additional mile Allied forces advance pushes their air cover closer to the operational limit, where fighters must turn back for refueling before completing protection missions. The solution exists in Morrison's equipment manifest: 60 bulldozers, 40 carry-all scrapers, 30 motor graders, 20 gasoline-powered shovels, 15 steamrollers, 8 rock crushers, and 700 tons of square mesh track, a British development that most German engineers have never heard of and wouldn't believe worked even if they studied its specifications. Square mesh track: 3-inch squares of heavy-gauge wire welded into rolls that unwind like industrial carpet. Each section weighs approximately 1/10 what pierced steel plank weighs, making it light enough to transport across the English Channel in landing craft already overloaded with ammunition and medical supplies. The material's genius lies in its simplicity. It doesn't create a paved surface. It reinforces existing soil just enough to support aircraft that weigh 20,000 pounds during takeoff and landing. The catch? Nobody knows if it actually works under combat conditions. The engineers tested SMT in England during training exercises. They laid test strips and drove trucks across them. They calculated load-bearing capacity and soil compression rates. But nobody landed a fully loaded Thunderbolt travelling 95 miles per hour onto SMT laid over Norman clay that's been pulverised by 6 weeks of naval bombardment. Morrison's orders are explicit. If the landing strip fails, aircraft will crash, pilots will die. The invasion timetable will slip because tactical air support cannot operate from bases 300 miles away in England. The burden of proof rests on whether 700 tons of British wire mesh can handle American fighters returning from combat with battle damage and low fuel. The reconnaissance group begins work at 1000 hours on June 8th. 50 men pushed forward behind American infantry, still clearing German snipers from hedgerows 600 yards ahead. Their mission seems absurdly simple. Walk across Norman pasture and identify relatively flat terrain 1,500 meters long by 100 meters wide. That's not mined, not pre-sighted by German artillery, and accessible to heavy construction equipment. Technical Sergeant James Chen, a former surveyor from San Francisco, leads the advance party with instruments that seem comically inadequate for battlefield conditions. A transit level, measuring chains, stakes and string. The tools haven't changed since Roman engineers built roads 2,000 years earlier, but Chen's methodology represents distinctly American pragmatism. He's not selecting ideal terrain, he's identifying terrain that's good enough. The criteria evolved through Pacific theater experience where aviation engineers built over 40 airfields on islands where flat ground meant anything with less than 7-degree slope. Chen learned at Guadalcanal that perfect runways were for military academies. Combat strips needed 3 characteristics: relative level, relatively dry, relatively unobstructed. The definition of relatively expanded with every island where Marines needed air support yesterday. By 1400 hours, Chen marks the runway centerline, stakes every 100 meters connected by string that runs northwest to southeast, aligned to prevailing wind patterns that British meteorological analysis predicted would dominate the Norman coastline during June and July. The runway bearing reads 85 degrees, close enough to the preferred 90 degrees that crosswind landing won't exceed fighter aircraft limitations. Captain Morrison approves the site at 1500 hours. The decision takes 12 minutes. German engineering standards would require weeks of soil analysis, drainage, surveys, and formal approval through multiple command levels. Morrison evaluates one factor: can his bulldozers reach this location without getting stuck in the tank traps and flooded ditches German defenders dug to prevent exactly this kind of rapid advance? The answer is yes. Barely. The approach path crosses 2 hedgerows that 3rd Infantry Division cleared this morning and 1 irrigation ditch that's currently more mud than water. Morrison's equipment can bridge the ditch with debris from nearby ruined buildings. The hedges are simply obstacles to remove, and his battalion includes men who cleared forests in Oregon and Tennessee before the war taught them to clear German defenses. At 1600 hours, the first bulldozer crosses the start line. Caterpillar D7, 15-ton diesel-powered earth mover driven by Corporal William Big Bill Hayes of Mobile, Alabama. Before Pearl Harbor, Hayes operated construction equipment, building bridges across the Tennessee Valley for Roosevelt's public works programs. He knows exactly how hard you can push a bulldozer before the transmission overheats or the blade mechanism fails. More importantly, he understands that construction timelines in combat aren't requests, they're survival requirements. The blade drops. 15 tons of American steel begins pushing Norman topsoil. Hayes starts at the runway's northern end, making a first pass that establishes the rough grade. Behind him, 3 more D7s follow in echelon formation, each offset 20 meters from the previous bulldozer. The parallel passes create a scraped corridor, 40 meters wide, that will eventually expand to 100 meters once the initial grading proves the soil composition can support the work. This initial phase reveals what makes American aviation engineering unique. Hayes isn't following detailed blueprints or precise elevation specifications. He's grading by eye and experience, maintaining a rough level surface that sacrifices perfection for speed. The bulldozer blades shave approximately 6 inches of topsoil, removing grass and organic matter that would compress unpredictably under aircraft loads. The removed soil gets pushed to the runway edges, where it forms natural berms that will help define the landing area for pilots approaching in poor visibility. By 1800 hours, 4 bulldozers have made 8 complete passes along the runway's length. 12,000 meters of earth have been moved, creating a rough corridor that starts resembling something aircraft might conceivably land on. Except it's not remotely ready. The scraped surface is loose dirt, churned by bulldozer treads into a consistency somewhere between mud and dry clay depending on depth. A fighter attempting to land on this surface would sink to its wheel hubs and nose over, killing the pilot and destroying the aircraft. The carry-all scrapers arrive as the bulldozers complete their work. These machines look like prehistoric monsters, a blade suspended between 2 enormous wheels, towed by a separate tractor. The blade scrapes soil, accumulates it in a hopper, then deposits it wherever the operator chooses. They're essentially mobile earth containers that can move 12 cubic yards of dirt in a single pass. Sergeant Thomas O'Brien of Boston commands the scraper teams. His civilian career involved building subway tunnels beneath Massachusetts, teaching him that Earth moves according to physics, not construction schedules. The scraper's job is precise grading, removing high spots and filling low spots until the runway surface varies no more than 6 inches across its entire length. This level of precision would be inadequate for permanent airfields. For combat strips, it's perfect. The scraping continues through sunset. The 819th has portable lighting generators powering floodlights that transform the construction site into an island of light surrounded by darkness, where German positions wait 300 yards away. The artificial illumination feels exposed, vulnerable. Morrison knows every German observer within 2 miles can see exactly where his battalion is working. He also knows that German artillery ammunition is rationed after 6 weeks of preparatory bombardment, and enemy gunners aren't wasting shells on construction sites when Allied infantry threatens their primary defensive positions. By 2200 hours on June 8th, the rough grading is complete. 1,500 meters of scraped earth, leveled to within acceptable tolerance, ready for the critical phase that will determine whether this insane timeline produces a functional runway or an elaborately graded drainage ditch. The steamrollers begin at midnight. 3 massive machines, each weighing 10 tons, powered by diesel engines that generate enough torque to compress soil to density that approaches natural stone. The roller operators work in darkness, punctuated by floodlights, making overlapping passes that gradually compact the loose soil into something approaching load-bearing surface. This phase cannot be rushed. If the soil isn't sufficiently compacted, it will develop ruts and depressions when heavy aircraft land. If it's overcompacted, the soil becomes concrete hard but so rigid that SMT anchoring stakes cannot penetrate deep enough to secure the wire mesh. The roller operators rely on experience gained at training bases in England, where they practiced this exact sequence on terrain deliberately chosen to simulate Norman soil conditions. By 0 to 400 hours on June 9th, the compaction is complete. The runway surface looks like a hard-packed dirt road, smooth enough that you could land a light aircraft if you were desperate or stupid. But P-47s weighing 10 tons aren't light aircraft. They need something stronger. The square mesh track arrives on 6x6 trucks at 0530. 700 tons of British wire mesh rolled into sections 4 meters wide and 100 meters long. Each roll weighs approximately 350 pounds, light enough that 4 men can move it, heavy enough that it requires coordination to unroll without tangling. Staff Sergeant Michael Rodriguez from San Antonio, Texas, supervises the SMT installation. His background includes precisely 0 construction experience. Before the war, Rodriguez worked as a high school mathematics teacher, specializing in geometry and practical problem solving. The Army discovered his talent for spatial reasoning and assigned him to airfield construction, where most problems reduced to geometry, how to cover maximum area with minimum material in minimum time. Rodriguez calculated the SMT requirements in England before the invasion. A 1,500-metre runway requires exactly 18 sections of mesh laid perpendicular to the centerline, overlapping by 1 metre on each edge to prevent gaps where aircraft wheels might drop through. Mesh sections must be anchored every 10 metres with steel stakes driven 45 centimetres into the compacted soil. Total stake requirement, 2,700, preloaded on trucks and ready for installation. The installation teams work in coordinated groups. 8 men per section. 2 teams unrolling from opposite ends simultaneously to prevent mesh from billowing in the wind. 4 teams driving stakes at marked intervals. The work demands precision and synchronized timing that transforms construction into something resembling military drill. By 0 to 800 hours, on June 9th, 1/3 of the runway is covered. The wire mesh lies flat against compacted soil, anchored against wind and weather. Infantry troops passing the construction site stop to watch with expressions mixing confusion and respect. They've seen bridges built under fire, roads repaired overnight, but transforming empty pasture into functional runway in less than 24 hours seems to violate basic assumptions about how military logistics operates. By 1200 hours, the entire runway is surfaced. 1,500 metres of square mesh track, anchored and ready. Morrison walks the full length, checking for high spots, loose sections, or areas where stakes didn't penetrate sufficiently. He finds 6 problem areas and orders immediate repairs. By 1300 hours, the emergency landing strip designated ELSA-1 is technically complete. Technical completion doesn't mean operational. Nobody knows if the runway actually works until aircraft land on it. Morrison requests permission to test with an observation plane. Division headquarters denies the request. Observation aircraft are scarce, and nobody's willing to risk one testing experimental runway construction. If ELSA-1 works, they'll discover that when a damaged fighter needs emergency landing, if it doesn't work, they'll discover that when the fighter crashes. The uncertainty gnaws at Morrison. He's built something that appears functional. The mathematics suggest it should work. British engineers insist SMT can handle single-engine fighter loads. But combat aviation accepts no margin for should and appears. Lives depend on whether his calculations and his team's craftsmanship meet specifications that won't be verified until somebody dies or survives based on whether the runway holds. June 12, 1944, 0930. A damaged P-47 Thunderbolt approaches, ELSA-1, with a smoking engine and partially deployed landing gear. The pilot, Lieutenant Michael Chen of the 366th Fighter Group, transmitted Mayday 15 minutes earlier after ground fire damaged his cooling system during a strafing run against German supply columns. Morrison stands at the runway's edge with binoculars, watching the crippled fighter line up for approach. The Thunderbolt is too heavy. Combat damage added weight from battle damage, and the asymmetric landing gear means uneven load distribution. If the runway fails, Chen will cartwheel across the French countryside in a fireball of aviation fuel and torn aluminum. The wheels touch at 95 miles per hour. The SMT compresses, flexes, holds. The Thunderbolt rolls down the center line, emergency brakes smoking, slowing gradually through momentum that tests every stake Rodriguez's teams drove into Norman clay. At 700 meters, the fighter stops. Morrison releases breath he didn't know he was holding. The runway works. More importantly, Chen climbs from the cockpit and walks away from an aircraft that should have killed him. ELSA-1 graduated from theoretical construction to operational facility in the 90 seconds. It took a damaged fighter to prove that American engineering can build runways faster than German doctrine believes possible. By 1300 hours, General Henry Hap Arnold, commanding general of the United States Army Air Forces, lands at ELSA-1 during an inspection tour from England. His C-47 transport touches down on the same mesh that held Chen's fighter 4 hours earlier. Arnold spends 20 minutes touring the site, asking Morrison detailed questions about construction methods and timeline. Before departing, Arnold approves immediate expansion of the strip into Advanced Landing Ground A1, capable of handling full fighter group operations. The expansion begins immediately. The 819th has 6 days to transform a 1,500-meter emergency strip into a full fighter base with fuel storage, ammunition dumps, maintenance facilities, and enough operational capacity to support 75 aircraft flying 4 sorties daily. The timeline seems ambitious until Morrison reminds his exhausted engineers that they just built a functional runway in 36 hours, while German positions were still in weapons range. By June 18th, Advanced Landing Ground A1 is fully operational. The 366th Fighter Group relocated from Thruxton, England, establishing the first American fighter squadron operating from continental Europe. Their P-47s begin flying ground support missions with response times measured in minutes, rather than the 45 minutes required for aircraft based across the English Channel. The German Luftwaffe's reconnaissance photographs from June 19th show what appears to be impossible. An American fighter base operating from terrain that was empty farmland 13 days earlier. Lieutenant Zimmermann studies the images with growing comprehension that American aviation engineering operates according to principles that German military education never anticipated. What Zimmermann still cannot grasp, what Wehrmacht intelligence will struggle to understand throughout the entire Normandy campaign, is that A1 isn't exceptional. It's the template. 9 more advanced landing grounds will open in the American sector within 3 weeks. British engineering units are constructing additional 17 airfields using similar rapid construction methods. Speed isn't an isolated achievement. It's systematic capability born from industrial methods applied to military problems with American characteristic disregard for traditional limitations. June 24, 1944, Paris. Luftflotte 3 Headquarters. Field Marshal Hugo Sperle convenes an emergency conference with intelligence staff who cannot explain how Allied tactical aviation has expanded from 0 continental bases to 23 operational airfields in 18 days. The maps on Sperle's wall tell a story that violates everything German military planning assumed about amphibious warfare logistics. Red pins mark confirmed Allied airfields. Each pin represents a fighter base, supporting 30 to 75 aircraft, conducting 4 to 6 sorties daily. The mathematics are devastating. 23 airfields multiplied by average 50 aircraft equals approximately 1,150 Allied fighters operating from forward positions. German aerial reconnaissance counted fewer than 300 Luftwaffe aircraft available for all missions across the entire Normandy sector. But numbers alone don't capture what makes Sperle's situation hopeless. German fighters operating from bases near Paris face 120-kilometer flights to reach the front lines. That distance consumes fuel, limits combat time over target, and exhausts pilots who must navigate through Allied fighter patrols that now control Norman airspace. American P-47s flying from bases 8 kilometers behind the beachhead face 5-minute flights to support ground forces. They can respond to close air support requests faster than German battalion commanders can communicate orders to their forward companies. Major Ernst Hoffmann, Sperle's intelligence chief, presents analysis based on captured Allied engineering equipment and prisoner interrogations. The Americans, Hoffmann reports, employ construction methods that prioritize speed over permanence. Their airfields aren't built to last. They're built to operate immediately, then be abandoned when ground forces advance beyond the tactical radius that makes forward positions valuable. This philosophy contradicts German engineering tradition, where military installations were constructed to standards approaching peacetime infrastructure. Luftwaffe airfields featured concrete runways, permanent hangars, sophisticated drainage systems, and facilities designed to support operations for years. American advanced landing grounds feature wire mesh runways, tent facilities, and minimal infrastructure that can be constructed in 1 week and abandoned without regret. The strategic implication troubles Hoffmann more than the tactical numbers. If Americans can build airfields this quickly, German forces cannot create defensive lines beyond Allied tactical air support range. Every kilometer Wehrmacht. Units retreat. American aviation engineers advance with them, establishing new forward bases that maintain constant pressure. The Luftwaffe cannot bomb these temporary installations effectively because by the time reconnaissance identifies a target and mission planning allocates scarce bomber resources, the airfield has either been abandoned or reinforced with anti-aircraft defenses that make attacks prohibitively expensive. Spurler demands solutions. Hoffman provides an honest assessment that resembles military obituary more than tactical planning. The Luftwaffe must contest Allied air superiority through offensive operations against these forward airfields. But offensive operations require fuel that's increasingly scarce after Allied bombing systematically destroyed French refineries and transportation networks. They require pilots that Germany can no longer replace after losing 35 aircraft daily throughout April and May. Most critically, they require accepting losses that will deplete remaining German air strength for uncertain gain against targets that Americans can rebuild in 1 week. The conference ends with Spurler's acknowledgement that Luftflotte 3 has effectively lost the air battle for Normandy. German fighters will continue operating in defensive roles, protecting critical transportation nodes and headquarters installations. But contesting Allied tactical air supremacy over the beachhead is no longer feasible. The Americans built their airfields too quickly, too close to the front lines, and in sufficient numbers that eliminating them would require air offensive capability that Germany hasn't possessed since 1943. Back in Normandy, the 819th Engineer Aviation Battalion begins work on their third airfield. The site near Beuzeville-aux-Plaines offers better natural drainage than previous locations, but presents new challenges. German artillery at Carentan, 6 kilometers south, can reach the construction site with 105mm howitzers. Building an airfield under intermittent bombardment requires accepting casualties that peacetime construction would consider criminal negligence. Captain Morrison adapts procedures developed at previous sites. Bulldozer operators work in staggered shifts, maximizing progress while minimizing personnel exposure during predictable German bombardment windows. Morning artillery barrages typically occur between 0 to 700 and 0 to 800 hours, targeting areas where American activity was visible the previous day. Morrison schedules heavy equipment operations to begin at 0830 after German gunners exhaust their limited daily ammunition allocation on empty fields. The psychological toll of construction under fire affects his men differently than combat infantry. Soldiers facing direct enemy fire can return fire, take cover, or maneuver to better positions. Engineers grading runways under artillery bombardment can only continue working or stop working. Stopping means failing the mission. Continuing means accepting that random German shells might land on a bulldozer or strike a fuel truck loaded with aviation gasoline. Private First Class James Sullivan from Boston operates a bulldozer during the Beuzeville construction when a 105mm shell lands 40 meters away. The concussion flips the 15-ton machine onto its side, throwing Sullivan clear but destroying the bulldozer and creating a crater 3 meters wide directly in the planned runway path. Sullivan suffers a broken wrist. The bulldozer is a total loss. The crater becomes just another obstacle to fill. Morrison doesn't suspend operations. He redirects scrapers to fill the crater, while maintenance crews cannibalize parts from Sullivan's destroyed bulldozer to repair 2 other machines suffering mechanical failures. By that evening, the crater is gone, filled with rubble from nearby destroyed buildings and compacted until it's indistinguishable from surrounding terrain. Advanced Landing Ground A6 opens on schedule, June 14th, 8 days after D-Day. The construction tempo accelerates through late June as additional engineer aviation battalions arrive from England. The 826th, 832nd, and 834th battalions join operations, each assigned to different sectors where infantry advances create opportunities for forward airfield placement. Competition develops between battalions over which unit can complete construction fastest while maintaining quality standards that keep pilots alive. The 834th Engineer Aviation Battalion sets the record at Cardenville. Construction begins June 17th at 0 to 600 hours. By June 18th at 1800 hours, Advanced Landing Ground A3 is operational 36 hours from first bulldozer to first landing. The accomplishment requires near-perfect execution, favorable soil conditions, no German interference, optimal weather, and battalion personnel working continuous shifts with 4-hour sleep rotations that leave everyone exhausted but the airfield functional. German intelligence finally captures intact square mesh track sections in late June, during a brief counterattack that overruns a partially completed American airfield near Saint-Lô. Wehrmacht engineers examine the wire mesh with professional confusion. The material appears impossibly flimsy for supporting 10-ton aircraft. Laboratory testing confirms the mesh alone cannot bear such loads. Its function is soil reinforcement. The wire distributes aircraft weight across sufficient surface area that underlying compacted earth carries the actual load. The analysis reaches Berlin, where Reichsmarschall Hermann Göring dismisses the findings as Allied deception. Göring insists proper airfields require concrete runways and permanent infrastructure. The idea that enemies could operate combat aircraft from wire mesh laid over compressed dirt seems like propaganda designed to demoralize German defenders. His refusal to accept intelligence assessment means Wehrmacht forces receive no guidance on countering American rapid airfield construction throughout the Normandy campaign. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By July 1st, 31 American and British advanced landing grounds operated in Normandy. The concentration approaches 1 airfield per 12 square kilometers of liberated territory. Allied air commanders can position fighter groups based on tactical requirements rather than logistical constraints. Ground attack aircraft respond to support requests within 8 minutes average from identification of target to first bomb release. German forces moving in daylight face near certain attacks by fighter bombers that seem omnipresent because they're based minutes away rather than hours away. The operational advantage extends beyond direct combat power. Allied photo reconnaissance aircraft operating from forward bases provide battlefield intelligence with speed that transforms tactical planning. Morning reconnaissance missions photograph German positions. Film reaches intelligence analysts by noon. Target packages are distributed to fighter-bomber squadrons by 1400 hours. Strike missions occur before 1600 hours. The cycle from reconnaissance to strike that previously required 24 to 48 hours now completes in 6 hours. German counterattacks face systematic disadvantage. Wehrmacht units concentrating for assault are identified during morning reconnaissance and attacked by mid-afternoon before attacks can launch. German supply columns moving ammunition and fuel forward face continuous interdiction because Allied fighters orbit above suspected approach routes, diving on any vehicle, movement. Artillery positions that reveal themselves by firing become immediate targets for airstrikes that arrive faster than German crews can relocate their guns. The cumulative effect creates battlefield conditions where German forces cannot operate effectively during daylight. Movement happens at night. Resupply occurs after dark. Even headquarters communications are restricted because radio transmissions during the day provide targeting data for Allied aircraft that can reach any location in the beachhead within 15 minutes. The Normandy battlefield becomes divided between Allied day and German night. Allied forces advance under continuous air cover during daylight hours, while German forces conduct limited operations after sunset, when Allied fighters return to their bases 8 kilometers behind the front lines. Technical Sergeant Michael Rodriguez analyzes advanced landing ground performance data in late July, compiling statistics that will influence American military aviation engineering for the next 80 years. The data confirms that SMT runways handle fighter operations more effectively than anticipated. Average runway lifespan before maintenance required: 327 sorties. Maintenance required: stake replacement where high traffic areas develop loose sections. Average maintenance time: 4 hours for a crew of 12 personnel. The numbers validate rapid construction philosophy. A runway built in 1 week and operational for 6 weeks before requiring relocation provides better tactical value than a concrete runway requiring 6 months construction. That's obsolete before completion, because front lines advanced 100 kilometers during construction period. Rodriguez's analysis influences post-war American military engineering doctrine that prioritizes operational flexibility over permanent infrastructure. The Corentin Airfield, designated Advanced Landing Ground A-10, presents unique construction challenges that demonstrate adapted American methodology. The site was captured June 12, only 9 days after D-Day, but sits within German artillery range from 3 directions. The 826th Engineer Aviation Battalion must build a 1,500-meter runway, while German 105mm and 155mm guns can target the construction site. Major Robert Chen, commanding the 826th, implements counter-battery construction tactics. His engineers work during German artillery quiet periods and immediately take cover when fire begins. Construction equipment sits idle during bombardments, but crews remain within sprinting distance. When shooting stops, work resumes without waiting for all clear signals. The rhythm becomes routine: work 15 minutes, take cover for 5 minutes, work 20 minutes, take cover for 8 minutes. The irregular pattern prevents German gunners from timing bombardments to maximize casualties. By June 19th, 4 days after construction began, A-10 was operational. The timeline would be impossible under peacetime construction standards, where worker safety regulations prohibit construction during active bombardment. Combat engineering accepts casualties as operational cost. The 826th lost 6 killed and 14 wounded during A-10 construction. Civilian construction projects in America would shut down after single fatality. Military engineering considers 6 dead acceptable when alternative is ground forces lacking air support against German counterattacks. The human cost of rapid airfield construction receives minimal attention in official reports that emphasize operational achievements over personnel losses. Aviation engineer battalions suffer casualty rates comparable to infantry units during Normandy operations. The difference is that infantry casualties occur during combat against enemy soldiers. Engineer casualties occur while driving, bulldozers, unrolling wire mesh, or operating steamrollers that cannot maneuver like combat vehicles when artillery shells land nearby. Private First Class William Hayes, the bulldozer operator from Mobile, Alabama, survives 3 different artillery attacks during July airfield construction operations. The third attack kills his assistant driver and destroys his bulldozer with a direct hit 15 seconds after Hayes dismounts to check track tension. He transfers to a new machine and resumes work the next day because the battalion has 6 bulldozers operational and requires 8 to maintain the construction schedule. Hayes' personal fear becomes secondary to mission requirements that won't pause for psychological recovery. By mid-July, American aviation engineers have perfected rapid airfield construction into a systematic process that reduces chance and eliminates wasted effort. The standard template for advanced landing ground construction emerges through repeated experience. Day 1. Reconnaissance identifies suitable terrain. Bulldozers begin rough grading. Day 2. Scrapers complete fine grading. Steamrollers begin compression. Day 3. Final compression. SMT delivery to site. Day 4. SMT installation complete. Test landings verify operational status. Days 5 through 7. Support facilities constructed: fuel storage, ammunition dumps, maintenance areas, personnel tents. The 7-day template becomes the baseline standard that engineering battalions compete to beat. The 819th completes 1 airfield in 6 days. The 834th counters with 5-day construction at another site. The rivalry drives performance improvements but also creates pressure that leads to accidents when exhausted personnel make mistakes, operating heavy equipment after 72 hours continuous work. Captain Morrison confronts the balance between speed and safety during A-21 construction near Saint-Laurent-sur-Mer. His battalion is ahead of schedule, positioned to complete the airfield in 5 days and establish a new construction speed record. But his equipment operators are exhausted, making errors that will cause accidents if he maintains the pace. Morrison delays SMT installation by 12 hours to allow mandatory rest periods. The decision costs the record but prevents casualties that would have resulted from fatigued personnel operating steamrollers. The German July 20th assassination attempt against Hitler briefly raises hopes that Wehrmacht collapse might make additional airfield construction unnecessary. Allied intelligence suggests German command structure might disintegrate, leading to negotiated surrender. For 48 hours, aviation engineer battalions pause new construction projects, while headquarters evaluates whether forward airfield expansion remains necessary. Hitler's survival ends speculation. The war will continue. Airfield construction resumes with increased urgency because Operation Cobra, the massive breakout offensive scheduled for late July, requires maximum tactical air support. The plan calls for 1,800 heavy bombers, followed by fighter-bomber strikes against concentrated German positions, then armored breakthrough exploitation. Success demands forward air bases positioned to support rapid advance into the French interior. By July 24th, 39 American advanced landing grounds operated in Normandy. British engineering units have constructed 29 additional airfields in their sector. The combined total of 68 operational airfields, 1,700 meters behind front lines, gives Allied forces air superiority so complete that Luftwaffe appears almost absent from Normandy skies. German fighters attempt occasional reconnaissance missions, but face such overwhelming opposition that few aircraft return with usable intelligence. The airfield construction achievement extends beyond tactical aviation, transport. Aircraft begin using advanced landing grounds for casualty evacuation and critical supply delivery. C-47. Dakotas land at forward strips, unload ammunition and medical supplies, then depart carrying wounded soldiers who reach English hospitals within 90 minutes of being loaded aboard aircraft. The evacuation speed saves lives that would be lost during multi-hour ambulance transport to beach hospitals. The Germans attempted countermeasures against Allied airfield proliferation in late July. Luftwaffe bombers conduct night raids against suspected airfield locations, dropping fragmentation bombs across probable runway areas. The attacks achieve minimal effect because advanced landing grounds lack valuable permanent facilities to destroy. Bomb craters in SMT runways are repaired by engineer teams within hours, using techniques developed through months of practice. Fill the crater with earth, compact with portable rollers, replace damaged mesh sections, anchor new stakes, resume operations. One German raid against A-11 near Cardenville destroys 3 parked P-47s and kills 2 ground crew personnel. The attack is considered successful by Luftwaffe standards. By American standards, it's inconvenient. Replacement aircraft arrive from England within 24 hours. New ground crew personnel transfer from rear areas within 48 hours. The airfield itself suffered damage and was repaired in 6 hours. The disparity between German attack costs and American repair costs makes airfield targeting economically irrational. Luftwaffe bomber missions cost scarce aviation fuel, risk experienced bomber crews that Germany cannot replace, and achieve temporary disruption that American engineering units repair faster than German intelligence can confirm whether attacks succeeded. After 3 weeks of attempted airfield interdiction, Luftwaffe command abandons the campaign as resource waste that achieves insufficient results. Operation Cobra launches July 25th with air preparation that demonstrates why rapid airfield construction matters strategically. 1,800 American heavy bombers drop 4,700 tons of high explosives on German positions in 90-minute bombardment. 550 fighter bombers follow with strafing and bombing runs that continue throughout the day. The fighter bombers refuel and rearm at advanced landing grounds, positioned within a 10-kilometer radius of the target area. The proximity allows unprecedented sortie rates. Individual P-47 pilots fly 4 missions on Cobra's first day because flight time from base to target area is 8 minutes. Conventional airfield positioning would limit pilots to 2 sorties daily maximum because 45-minute flights from English bases exhaust pilots and consume fuel that limits combat time over target. Forward airfield positioning effectively doubles Allied close air support capability through logistics, rather than additional aircraft. German forces facing Cobra encounter tactical situations without historical precedent. Continuous air attack from rotating fighter-bomber formations that seem endless because they're based so close they can maintain station over the battlefield for extended periods. Wehrmacht commanders report to higher headquarters that American tactical aviation has achieved the effect of approaching artillery barrage constant, overwhelming, and impossible to counter with available German resources. By July 31st, Operation Cobra achieved a complete breakthrough. American armored divisions advanced 60 kilometers in 6 days, capturing the strategic town of Avranches and opening routes into Brittany and toward Paris. The advanced speed creates new problem for aviation engineers. Their forward airfields are now rear area installations too far from advancing front lines to provide effective close air support. The solution demonstrates American logistical sophistication that German planning never anticipated. Aviation engineer battalions leapfrog forward, constructing new advanced landing grounds ahead of previous sites becoming obsolete. The 819th begins work on A35 near Lessay, while A1 near Saint-Pierre-du-Mont transitions to casualty evacuation and supply delivery roles. Fighter groups relocate forward every 10 to 14 days, maintaining position relative to advancing ground forces. The leapfrog strategy requires coordination between ground forces capturing territory, engineer battalions constructing airfields, and fighter groups relocating to new bases while maintaining operational capability. The complexity would overwhelm militaries lacking American logistical infrastructure and communication systems. Aviation engineers develop mobile command posts that move with advancing infantry, identifying potential airfield sites during active combat operations rather than waiting for rear area security before beginning. Reconnaissance. By August 15th, 49 days after D-Day, Allied aviation engineers have constructed or rehabilitated 93 airfields in France. The construction rate averages approximately 2 airfields per day, a tempo that would require 18 months using pre-war peacetime construction methods. The achievement represents industrial warfare applied to military engineering systematic processes, specialized equipment, and trained personnel producing results through methodology rather than heroic individual effort. Lieutenant Klaus Zimmermann, the Luftwaffe intelligence officer who first reported impossible American airfield construction on June 7th, is captured by Allied forces during the Falaise Pocket Battle in mid-August. American intelligence officers interview him about German air operations in Normandy. Zimmermann's assessment is professionally honest. The Luftwaffe lost the air battle not through inferior aircraft or inadequate pilot training, but through logistical disadvantage created by American aviation engineering capability that Germany had no counter for. His final observation enters Allied intelligence reports almost verbatim. "We studied your aircraft. We analyzed your tactics. We calculated your production numbers. But we never understood that you could build airfields faster than we could bomb them. That was the advantage that made everything else irrelevant." September 5, 1944. Advanced landing ground A1, near Saint-Pierre-du-Mont, stands empty. The wire mesh runway that made history on June 9th as the first American operational airfield in continental Europe now serves no tactical purpose. Allied forces have advanced 200 kilometers east, positioning fighter groups near the German border, where proximity to Wehrmacht defensive lines provides maximum operational value. The airfield that astonished German intelligence officers and validated revolutionary construction methods has become obsolete. 90 days after opening, Captain Robert Morrison walks the abandoned runway on his final inspection before the 819th Engineer Aviation Battalion moves to new construction sites in Belgium. The square mesh track shows where from 3 months of continuous operations. Sections near the touchdown zone display compression patterns where thousands of fighter landings concentrated force on specific areas. Stakes have loosened in several locations where Norman clay softened during August rains, but the runway remains fundamentally intact, capable of supporting operations if a tactical situation is required. Morrison calculates in his engineer's mind what this installation represents. 700 tons of steel mesh, 42,000 man-hours of construction labor, 6 casualties during initial construction and subsequent maintenance, 397 aircraft landings and takeoffs before the 366th Fighter Group relocated to A-72 near Laon. The statistics reduce to cold efficiency ratios that military planners will study for decades: cost per operational day, casualties per 1,000 sorties supported, construction time versus operational lifespan. But Morrison remembers details that won't appear in official reports. Private Sullivan's broken wrist when German artillery destroyed his bulldozer. The morning Technical Sergeant Chen's survey team worked 200 yards from German positions that could have killed them with a single machine gun burst. The night his men laid SMT sections in darkness while hearing German tanks moving somewhere beyond the hedgerows. The human cost of building airfields at combat tempo cannot be captured in efficiency statistics. The 819th departs for Belgium, leaving A1 to French farmers who will gradually reclaim their pastures. Some SMT sections will be salvaged for other uses: fencing material, reinforcement for concrete, improvised building supplies, in a nation where war destroyed infrastructure faster than peacetime reconstruction can replace it. Most of the mesh will remain in place for years, slowly rusting into the Norman soil that briefly served as runway for American fighters. The pattern repeats across Normandy as autumn arrives. Advanced landing grounds that seemed critically important in June become excess infrastructure in September. Allied aviation engineers constructed 93 airfields in France during the 3 months following D-Day. By October, fewer than 30 remain operationally necessary. The abandoned sites scatter across Norman and Breton countryside, monuments to temporary military necessity that transformed farmland into runways, then returned it to agriculture with mechanical efficiency. German forces retreating toward the Rhine River face continuous pressure from Allied tactical aviation that maintains position relative to advancing ground forces through systematic airfield construction. The 8th, the 119th, and sister engineer aviation battalions constructed new, advanced landing grounds in Belgium, Luxembourg, and eastern France at the same rapid pace that characterized Normandy operations. Wehrmacht intelligence officers monitoring Allied movements report that American fighter bases appear ahead of German expectations, suggesting aviation engineers operate within advancing combat formations rather than following behind secure rear areas. The observation is correct. Aviation engineer battalions have integrated with frontline units to a degree that blurs distinction between combat forces and support elements. Engineers conduct terrain reconnaissance during active operations, sometimes arriving at potential airfield sites before infantry completely secures the area. The aggressive forward positioning creates casualties, but maintains tactical advantage that German forces cannot counter. By mid-September, 9th Engineer Command had placed 80 additional airfields in operation across France, Belgium, and Luxembourg. The construction pace exceeds even Normandy operations, because captured German airfields provide existing infrastructure that requires rehabilitation rather than new construction. Aviation engineers discover that repairing bomb-damaged concrete runways takes less time than building new SMT airfields when German facilities include serviceable drainage systems and dispersal areas. The winter of 1944 through 1945 tested airfield construction methods in ways Normandy's summer weather never challenged. Square, mesh track, and prefabricated Hessian surfacing, the primary materials for rapid construction, both fail under conditions of extended freezing temperatures and heavy precipitation. The wire mesh becomes brittle in extreme cold. The burlap surface saturated with water freezes into rigid sheets that crack under aircraft loads. Runways that functioned flawlessly during summer months become unusable during winter storms. Pierced steel plank emerges as the only material capable of handling winter operations. The steel planking weighs 3 times what SMT weighs and requires substantially more time to install, but PSP maintains structural integrity regardless of weather conditions. Aviation engineer battalions shift construction priorities, installing PSP at airfields intended for winter operations while abandoning SMT fields that cannot handle seasonal conditions. The material transition demonstrates American logistical flexibility that German forces never achieve. Engineers identify performance limitations in preferred construction methods. The supply system delivers alternative materials. Construction procedures adapt to new requirements. Operations continue without significant disruption. The systematic problem-solving approach reflects industrial methodology applied to military challenges. Identify issues, implement solutions, measure results, refine processes. The Rhine River, Crossing in March 1945 requires aviation engineering support that exceeds anything attempted during Normandy operations. Allied forces must establish air superiority over German heartland while advancing through terrain where every bridge has been destroyed and every potential airfield site falls within German artillery range. Aviation engineers construct supply and evacuation strips under direct fire, accepting casualty rates that approach infantry levels during intense combat periods. Private First Class William Hayes, still operating bulldozers for the 819th Engineer Aviation Battalion, participated in construction of A-97 near Wesel, Germany. The site sits within 3 kilometers of German defensive positions that include 88mm anti-aircraft guns repurposed for direct fire against ground targets. Hayes and his fellow operators work in 15-minute increments between artillery barrages that force evacuation to covered positions. The construction takes 9 days instead of the standard 7 because German interference prevents continuous work. The battalion suffered 12 casualties, including 3 killed during the project. But A-97 opened on schedule, providing a forward base for tactical fighters supporting infantry crossing the Rhine against Wehrmacht units, making their final defensive stand. By May 8, 1945, when German forces surrendered unconditionally, American aviation engineers had constructed or rehabilitated 280 airfields in the European theatre of operations. The total represents one airfield completed every 43 hours during the 11 months from D-Day to VE Day. The construction tempo has no historical precedent and will not be matched during subsequent American military operations in Korea, Vietnam, or the Middle East. The final statistics compiled by IX Engineer Command tell the story in numbers that military historians study for generations. 280 airfields, 43,000 sorties supported during peak operational periods. Construction time averaging 6.8 days per advanced landing ground using SMT surfacing. 16.3 days for PSP installations. Casualty rate of 4.7 per thousand man-days during combat construction operations. But statistics cannot capture what the achievement meant for Allied victory in Europe. Tactical air supremacy, enabled by forward airfield positioning, allowed ground forces to advance against German opposition that would have been impossible without continuous close air support. Wehrmacht commanders consistently reported that Allied aviation prevented daylight operations, disrupted supply lines, and destroyed counterattack formations before they could engage Allied ground units. The air superiority that made these tactical effects possible depended absolutely on aviation engineers' capability to construct airfields faster than German forces could retreat. Technical Sergeant Michael Rodriguez, the mathematics teacher turned airfield construction specialist, returned to San Antonio in November 1945 after being discharged from the Army. He resumes teaching geometry and practical problem-solving to high school students who seem impossibly young after 3 years building runways under fire in France, Belgium, and Germany. Rodriguez rarely discusses his war service, not from trauma, but because civilian life provides no context for explaining how wire mesh and compressed dirt can support 10-ton aircraft landing at 95 miles per hour. The knowledge Rodriguez gained about rapid construction methods influenced American civil engineering for decades. Post-war airport construction adopts principles learned through military necessity, prioritize operational capability over aesthetic considerations, use prefabricated materials where possible, design for rapid expansion rather than permanent perfection. The practical methodology that built 280 combat airfields in 11 months shapes civilian infrastructure projects across America during the 1950s and 1960s. Captain Morrison received the Legion of Merit for his leadership of the 819th Engineer Aviation Battalion during European operations. The citation mentions specific airfields constructed under fire and notes casualty figures that Morrison wishes were lower. He returns to civilian life as a construction engineer in Connecticut, building highways and industrial facilities using expertise gained, pushing Norman clay into runways, while German artillery tried to kill his bulldozer operators. Morrison never fully reconciles the contradiction between pride in his battalion's achievements and grief over the men who died building temporary airfields that were abandoned months after completion. 6 personnel killed during A1 construction. 8 more during subsequent projects. 14 total casualties in a unit that existed to support aviation operations, not engage enemy forces directly. The deaths seem to lack the glory associated with combat casualties while carrying identical finality. The abandoned advanced landing grounds scattered across France become a curiosity for local populations who reclaim land that briefly served American military purposes. Farmers discover that SMT sections make excellent fencing material. The wire mesh resists corrosion better than traditional fencing and requires no maintenance beyond occasional stake replacement. By the 1950s, kilometers of former runway surface provided property boundaries across Normandy, Brittany, and eastern France. Occasional sections of pierced steel plank remain visible in French countryside, even into the 21st century. The steel planking proves remarkably durable, maintaining structural integrity decades after its military purpose ended. Historians and battlefield tourists hunt these remnants as physical evidence of American aviation engineering achievement that changed warfare's fundamental nature. The doctrinal legacy extends far beyond physical artifacts. American military engineering establishes principles that influence construction operations for the next 80 years. Speed matters more than permanence when a tactical situation demands immediate capability. Prefabricated materials enable rapid deployment of transportation infrastructure and can deliver them to forward areas. Personnel training and equipment quality determine construction success more than elaborate planning or sophisticated design. The United States Air Force adopts rapid airfield damage repair procedures, directly descended from World War II aviation engineer experience. Modern combat engineers train to restore bomb-damaged runways, using techniques that Morrison's battalion pioneered in Normandy: fill craters, compact earth, install temporary surfacing, resume operations. The methodology assumes that airfields will be damaged and prioritizes rapid repair over preventing damage through hardening or dispersion. Soviet military observers studying American operations in Western Europe recognize that aviation engineering capability provides an asymmetric advantage that material numbers alone cannot overcome. Post-war Soviet military doctrine emphasizes airfield construction as a critical enabler for tactical aviation, leading to development of specialized engineer units modeled on American aviation engineer battalions. The Red Army's capability to construct forward air bases during hypothetical European conflict derives directly from lessons learned watching American engineers build Normandy airfields in June 1944. The Germans never develop equivalent capability. Wehrmacht engineering units continue operating according to traditional methodology that prioritizes permanent construction over rapid deployment. Luftwaffe airfields, constructed during the war, feature concrete runways, permanent hangars, and infrastructure designed for extended operations. The facilities are superior to American temporary installations in every measure except the one that matters most: time required for construction. By the time German engineers complete the permanent airfield, the tactical situation has changed and the location is no longer valuable. Lieutenant Klaus Zimmermann, the Luftwaffe intelligence officer captured at Falaise, provides detailed assessment of German airfield engineering limitations during post-war interrogation. His analysis identifies fundamental philosophical differences between German and American approaches. German military tradition views infrastructure as a strategic asset requiring substantial investment and careful planning. American military pragmatism views infrastructure as a temporary tool that serves immediate tactical purpose, then becomes disposable when circumstances change. Neither approach is inherently superior. German permanent airfields provide better capability for extended operations when the tactical situation remains stable. American temporary installations provide flexibility when fluid battlefield conditions require constant adaptation. The difference is that World War II's Western Front, after June 1944, never provided stable conditions where German methodology's advantages could manifest. Allied forces advanced too rapidly, and American aviation engineers followed too closely for permanent installations to retain value. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe. The morning of June 7th, 1944, Lieutenant Klaus Zimmermann stared at reconnaissance photographs showing American fighters landing on runway that didn't exist 24 hours earlier. He knew the images revealed something important but lacked framework to understand what American aviation engineering actually meant for Wehrmacht's defensive capabilities. By September, after 3 months watching Allied airfields multiply faster than Luftwaffe could bomb them, Zimmermann understood. But understanding came too late to matter. The story of American rapid airfield construction in Normandy is not about heroic individuals or technological breakthrough. It's about systematic capability, trained personnel, specialized equipment, proven methodology, applied with industrial efficiency to military problem that demanded speed over perfection. Captain Morrison and the 819th Engineer Aviation Battalion didn't invent new construction techniques or revolutionary materials. They executed existing procedures with competent professionalism while accepting casualties that peacetime standards would consider intolerable. The achievement was making the possible routine. Building runways in 1 week wasn't miraculous when you had bulldozers, scrapers, rollers, and 700 tons of wire mesh. It was just very good construction management applied under circumstances where failure meant Allied soldiers dying from lack of air support. The engineers weren't heroes performing impossible tasks. They were skilled workers doing difficult jobs with adequate resources and clear understanding that speed mattered more than safety. History remembers D-Day for amphibious landings and infantry fighting on beaches. The victory depended equally on aviation engineers who transformed Norman pastures into fighter bases while German artillery tried to kill them. Without those runways built in June and July 1944, tactical air supremacy that enabled Allied breakout operations would have been impossible. The P-47s and P-51s that dominated Normandy skies operated from airfields that existed because Robert Morrison, William Hayes, Michael Rodriguez, and 800 other engineers worked through exhaustion and fear to prove that American industrial methodology could build runways faster than German military doctrine believed possible. The lesson transcends aviation engineering and illuminates broader truth about military capability. Victory often depends less on superior weapons or brilliant tactics than on unsexy logistics and competent execution. The Americans didn't win the air battle through better aircraft. German fighters were often superior. They won through systematic advantages in pilot training, fuel availability, maintenance capability, and airfield positioning. The last factor depended entirely on engineers willing to operate bulldozers within range of enemy artillery while building temporary installations that would be abandoned 3 months after completion. That's the impossible achievement that German generals couldn't believe. Not that Americans built airfields quickly, but that they built airfields quickly enough to maintain tactical advantage throughout an entire campaign. Despite constantly advancing front lines, the engineering feat required organizational capability that prioritized operational flexibility over permanent infrastructure, accepted that temporary solutions often provide better value than perfect solutions, and recognized that skilled workers with adequate equipment can accomplish remarkable results if given clear objectives and authority to execute. The abandoned runways scattered across French countryside are monuments not to American technological superiority, but to practical methodology that valued results over process. The wire mesh, rusting in Norman fields, supported fighters that helped win World War II, not through miraculous properties but through adequate function, achieved rapidly. That's what Lieutenant Klaus Zimmermann couldn't believe on June 7, 1944, when reconnaissance photographs showed the impossible. Americans had built an airfield overnight, not through magic but through competent engineering applied, with industrial efficiency, while accepting that some people would die making it happen. The human cost matters. Private First Class James Sullivan's broken wrist, the 6 personnel killed at A1, the 14 total casualties in Morrison's battalion, the hundreds of aviation engineers who died or were wounded building temporary installations across Europe. Their sacrifice enabled tactical advantages that military historians measure in strategic terms: air superiority, ground force mobility, logistical efficiency. But each advantage depended on individuals who operated construction equipment under fire because the mission required completion regardless of personal risk. That's the true story of American rapid airfield construction in Normandy, not a tale of impossible achievement by superhuman heroes, but an account of difficult work performed competently by skilled professionals who understood their job was building runways fast enough to matter tactically. They succeeded. The runways worked. Allied fighters dominated Normandy skies, and German generals who studied the reconnaissance photographs still couldn't quite believe that American engineers had transformed their military's logistics into operational advantage through nothing more mysterious than systematic capability applied with industrial efficiency. The war ended, the engineers went home, the temporary airfields became farmland again, but the lesson remained. Speed matters, flexibility matters. And sometimes the unsexy logistics of construction engineering determines victory more decisively than the glamorous tactics of aerial combat. That's what made Normandy's rapid airfield construction so remarkable, not that it was impossible, but that Americans made it routine.